So these next two example problems are going to be a little bit more challenging since we'll still be given a sequence, but now we're going to be given two formulas, explicit formulas for these sequences, and we need to determine if they're correct. So Haruka and Mustafa were asked to find an explicit formula for the sequence 4, 12, 36, and so on, where the first term should be g of 1. And before we look at their specific formulas, let's first generate our own formula and compare it to what they have. So remember the general explicit formula that if we have g of n, this will be equal to the first term multiplied by the common ratio r n minus 1 times. Like I said, r, that's our common ratio, the number that we will multiply to go from one term to the next in our sequence. And we just need to figure out these values. So for the common ratio, remember that you can always take one term and divide it by the term before it. So you can choose any term you want. Let's choose 36. And we'll divide it by the term before it, which is 12. And 12 goes into 36 3 times. But you can also see if you take 12 and divide it by 4, that you will also get 3. And of course, you can see our first term is 4 here. So just plugging in these numbers, since now we know a of 1 is 4, g of 1 is 4, we have that g of n, where now we're plugging in the nth term, is equal to that first term, 4, multiplied by our common ratio of 3 raised to the n minus 1 power. And we want to make sure this works, so let's check by choosing some term in the sequence and making sure this works by plugging in that term number. So let's do g of 4, since we know that the fourth term is 108. And if we just plug that in here to our formula, so g of 4 is 4 times 3 to the 4 minus 1 power, which is just 3. And 3 cubed is 27, so we get 4 times 27, which does multiply to 108. So we checked, and we can feel confident that this formula is the correct formula. So now that we have our own formula, let's compare it to what they have. And notice for Mustafa, you can see that that is incorrect right away, since it should be 4 times 3 to the n minus 1. Since this is the common ratio, and we found the common ratio to be 3. If it was 4, then it would go 4, 16, 64. Every step you'd be multiplying by 4. So Mustafa's is not correct, but we can check Haruka's formula, and we have 4 times 3 to the n power, but we know it should be the n minus 1 power. So this one is not correct either. Now, this approach of generating our own formula is not the only way to solve this problem. The other approach is to just plug in different n values and see if we actually get back that term. For instance, we know that when n is equal to 3, we get 36. So let's test that in both of these formulas just as a different way to approach the problem. So if we put in 3, we get 4 times 3 cubed. And we did that down below. We know this is 108. But that's the fourth term in our sequence, not the third one. So you can see that this is not correct. And for this one, we can do the same thing. Plug in 3. You get 4 times 4 to the third power, the second power, since we have 3 minus 1 for our exponent, which is 2. So this is really 4 multiplied 3 times, which is 64. And of course, it's supposed to be 36. So this is not correct either. And so this is just another way to verify that both of these are incorrect. So in this case, D would be the correct answer. And for the next problem, you can choose to do it either way. You can generate your own formula and then compare it, or you can just plug in values and see if you get back what the actual terms are in the sequence. And the second way is probably a little bit faster, but it's good practice to be able to generate your own formulas for these sequences. So let's look at another one. And in this one, we have Hiroki and Mapaya we're asked to find an explicit formula for the sequence 125, 25, 5, and so on, where the first term should be f of 1. And let's try the faster method for this. Let's just plug in n values and see if we get back what we expect. We could generate our own formula, and that might be a way to check. But if you want to do these quicker, we can just plug in different n values. And for this one, let's do the fourth term. So for n equals 4, we know that we should get f of 4 equals 1. So that's what we're looking for. But let's plug that into our formula here. So for Hiroki here, let's do that in blue. We have n equals 4. So f of 4 would be 625 multiplied by 1/5 to the 4th power. And 1/5 to the 4th power, if we multiply that out 4 times, you would have 1 in the numerator. Since 1 4 times is just 1. And 5 multiplied 4 times is 625. And we have 625 times 1 over 625, which is indeed 1. So it looks like Hiroki's formula is correct. And let's try it for Mapaya's formula here. So for that one, we're going to do the same thing. We're just plugging in 4 to our formula. And you can see this can't be correct because, well, it's the same term here for our common ratio raised to the nth power, but the starting number is different. So they can't both be equal to 1 here since they're different formulas. But we can try it anyways. We have 125 multiplied by 1/5 to the 4th power. And we know 1/5 to the 4th power is 625. So this just becomes 125 multiplied by 1 over 625, or 125 over 625. And this simplifies to 1/5. So that is incorrect. We were expecting to get 1 here. So what we found is that Hiroki's formula is correct, but Mapaya's is not. So it looks like choice letter A is the correct answer. And there's a couple ways to check this. You can either generate your own formula and compare it to Hiroki's, or you can just plug in another n value just to be certain. For instance, if we do n equals 3, we should get that f of 3 is equal to 5. So let's do that really quick. Plugging it into Hiroki's formula, we get 625 multiplied by 1 over 5 to the 3rd power, and this would be 1 over 125. So we have 625 over 125, which is 5. And that's what we expected. So for testing 2 different values, you can see that this definitely worked. And so we can feel confident that choice letter A is the correct answer.